Hello. So I thought in this video, first one for a long time, I would talk a bit about some of the cool semi-secret machines we have at UCL. For a couple of years now, I've been experimenting with hardware from Graphcore. Graphcore are a UK company. They build specialized processors for AI. And for, I think, about 2 years now, we've had two of these Pod 16, what they call an IPU Pod 16, at UCL, one of which is owned by UCL and one of which was funded by STFC. We've been in the process of rebuilding them over the last 3 months because they're experimental and they're not as well, let's be honest, they're not as well maintained by us as the production services. We've been moving them more into ARC because they were joint run with CS. We're slowly making them look more and more like ARC HPC systems. Um, so I thought I'd do a little demo and talk a bit about what they do. So um, effectively, this is a replacement for GPU computing, right? So the way we and pretty much everyone does machine learning at the moment is you buy graphics cards that are based off the same technology as you would buy for playing video games. But NVIDIA have created special classes of graphics cards which are server only, which don't actually do graphics. Targeted machine learning, so that's things like the A100s you'll see me use in other videos. And they're extremely powerful and very flexible. And NVIDIA has a very mature software stack for that. You can run machine learning stuff, but you can also run. They've got a Fortran compiler and stuff like that. But we've been experimenting with Graphcore because we like playing. It's worth investigating other options. And obviously, they're much earlier in the journey in terms of technology maturity than NVIDIA are. But what they do have is a set of libraries for C++ that you can use to program their accelerators. And they also have ports of like PyTorch and TensorFlow, things like that. Um, so what is a Graphcore Pod 16? Well, it's a server. One of our systems has a Dell server, the other one has a Lenovo server. It has four of these IPU boxes. Each of these IPU boxes has four accelerators inside it, hence Pod 16. Ours are the M2000 models, so they're, I think, one generation older than the current state of the art. Um, and they differ from GPUs in that they are multiple instruction, multiple data, as opposed to the sort of more SIMD operation of GPUs. So in a GPU, you can run lots of threads at the same time, but large chunks of those threads have to run lockstep. They have to execute the same instruction. That means you can't do branches and things like that. These systems are properly multiple instruction, multiple data. They do have a very odd sort of phasing of computation and communication all in step, which is a bit of a challenge to program. Um, the question you might ask yourself is, how do I program one of these? Well, it's not the friendliest thing. Um, those of you who know me a long time will know that we have a sort of canonical terrible way of calculating pi. My colleague Mose has coded that up for Graphcore. If you look in this directory, you end up with the main C++ program, which I'm going to be quite honest, looks fairly horrendous. You have to pull in a lot of external headers. You have to set up a lot of stuff. You then also have to have what they call their codelets, which is the actual code that runs on the accelerator. And then there's an additional problem, which is because these are targeted at machine learning, they are single precision only. That makes them extremely it's the nice way of saying this. They're less useful for general scientific work. And this really shows up in the Mandelbrot example, which is horribly inaccurate. So if we run this with, oops, it will build the code and then run it on by 0. We're running a lot of slices and we're getting very inaccurate results. And that's a function of being operating single precision. The algorithm does a lot of adding, multiplying small numbers. That makes it very bad at precision. But it works, right? What this is really targeted as machine learning. And so I thought the other example I've shown a lot to people is the fashion MNIST dataset and training it and using that to identify things and showing us the good old ankle boot. Now, you're pleased to know that this is effectively one of the examples in the Graphcore examples app. Bring up the right copy of Firefox. There we go. There's that. They've got a huge amount of documentation on here, including literally walking through doing this example. So I've pulled that together, ignoring sort of the graphical pieces of it, because we use our terminal. But we can run that on the IPU. So if I flip over to a terminal here, well, the downside of these machines is they don't have screens, so I'm sort of candidly using Tmux here. So I have indeed coded, pulled that code in. It's very similar to the code that we would have on the GPU and CPU systems. You load your data sets, both the training data set and the test data set. Set up a classification model. Do some training over the epochs using. One of the interesting things here is their version of Torch they call PopTorch, and that's some slightly more advanced feature than the normal PyTorch. So you can't just take your PyTorch code and run it. You will need to do some porting. Train the model, write it out to a file, and then do some inference on it. And then at the end, I've added in the bit that shows us the image of the ankle boot and checks that it's got that particular entry right. Right, if I go over to terminal where the environment's set up. So the other problem is there's a lot of environmental things you have to set up. If you look in my directory, my home directory, I've got a bunch of different shell scripts you need to source to make things work. For PopTorch, you need to pull in both. You need to create a virtual environment, into which you need to install. Oops. So as part of the software that comes with the Graphcore system, you get some wheels for PopTorch and for TensorFlow. So what you do is you create a virtual environment, you pip install this wheel, it brings in the other dependencies from PyPy, and then you have your virtual environment set up for running these things. Let me get to the right terminal. So you need to activate that environment. There's also a bunch of things which tell it where to find various bits of Poplar. So if we look at that, there's a step we have to do in our systems, which is to have a more up-to-date version of GCC. So we do that with the thing in Red Hat called SCLs. And then we need to set up the libraries for Poplar and PopArt. Having set all that up, we should be able to run our code. So it's the usual thing. It pulls fashion MNIST out of AWS. There's then a step which you don't have to do on GPU, which is that it actually compiles a graph of the model. And then it will do the usual loading in batches, train for 5 epochs. Then we'll do our inference step. And for inference, it needs to compile the graph so that it can be run on the IPUs. And for this simple example, that's a significant portion of the runtime. Right. And then the actual inference is extremely quick, and we're lucky to see that, yes, indeed, it has identified this picture as an ankle boot. Yeah, so we're going to be doing some more work with this in future. We've got some stuff about having nicer front ends to it, and some nicer frameworks. It's possible that this might be the foundation of a service in future, or it might not be. Depends on how well we get on with it. My colleague Mose has done some really amazing work that he's giving a talk about at JuliaCon. I'll put a link to that below in the description. Have a nice evening.